And I wouldn't have thought that
So
would come.
just to warn you, we're gonna go live now.
Okay.
Not that you'll get us taken down with that kind of language.
You didn't make it up.
It's a legitimate science experiment. It's an acronym.
Yeah.
All right, wave function collapsed. We exist. You have observed us, I think. Let's see. Yeah.
I saw a story that some YouTuber was like sick of getting their videos monetized by YouTube. And so they turned their videos into like music videos. Like they somehow like sang their things and then got them encoded as, in Content ID. They published them to Spotify or something so that Google couldn't make money off of their thing. And so I'm expecting that you're going to convert this to the musical space hangout or something in the future.
We all have to sing?
Well, no, but I don't think you need to do that. I think you could just encode the audio and then make that you can do a copyright ID on your own material. And then if YouTube plays it, then you can do a copyright content ID claim on your own material because you've laid down an audio fingerprint. That's really smart. The one that I like is the copyright deadlock. This is a thing that Jim Sterling, he's a video game reviewer, and he would put no ads on his stuff, and he would constantly get all of these copyright takedowns for because he'd play like a piece of video game or whatever. And so what he did is he would put in a couple of chunks of music from people that he knew would do a copyright claim on the video, but he would do enough of them where they would sort of lock each other out. And so then nobody, and he knew that they would not permit monetizing because these multiple ones had claimed copyright for it. Yeah, really smart. Yeah, I don't know whether it really worked, but yeah, he called it the copyright deadlock. But it's brutal. So I don't put any ads on any of my live streams now, and because there's too many ads. Like it's ridiculous. At this point, you do like an hour-long broadcast, and there'll be 9 ads in it. But now YouTube will put ads if you aren't part of the partner program. So like Weekly Space Hangout isn't part of the partner program, while Universe Today is. And so there could very well be ads on this program, and there's nothing we can do to stop it.
Yeah, it's just kind of started.
Yeah.
Sort of.
Yeah. So it's crazy. And there's no way for us to prevent it. I guess you could go watch this on Twitch, which it is being co-broadcast over on Twitch. But it's a bad, and they won't give you the revenue from it as a creator. So anyway, I'm going to say hi to some people in the chat. Hello to 6 Bob Holmes, Andrew Planet, Bill Smith, Bob Moeller, Brian Thomas, Christian Woodland, Corey S., David Dunn, David Fairweather, Horizon Brave, Ian Farquharan, Jay Broder, Johnny J, Johnny Z, Larry Beckham, Larry King, Nancy Graziano, Osha McIntyre, Ryan Schmitz, Scott Bragdon, Susan Hunter, Tom Van Scotter, and Zap Van Zappen. Hey everybody, welcome to the Weekly Space Hangout. Pre-show. Christian Woodland, yeah, I'm studying that stuff since I'll eventually do videos. Fun. Enjoy, Christian. We've talked. I don't know if we've talked about this here. I mean, I don't think I've ever had the same combination of people at the same time. But watching just the pandemonium over on Twitch, that everybody was getting all these copyright claims because they were playing copyright music behind their Twitch streams, and they're just shocked. And those of us on the YouTube side have just been.
Baby's first web stream.
Yeah, exactly. Yeah. Yeah, exactly. Like, we know that if you're walking down the street and someone is playing a piece of music in a bar, that's your problem, and you've got to hack that content out of your, you've got to make sure that doesn't show up in your show, because then all of your work is going to go to whatever music company owns it. David Dunn is asking how the Chinese language learning is going. There's 2 of us learning Chinese now. Alex, how's your Chinese going?
It's going okay.
Yeah.
The immersion really helps. I'm here in Taiwan for anyone who doesn't
Yeah.
know, and I've been over here for a few months, and it's great. I love learning Chinese.
Yeah.
Gonna have a
Yeah, me
Chinese
too.
language subsegment now
Sure.
I'm
Yeah.
not ready for that. I think
Yeah.
Fraser
for
might
the
be.
other
No.
billion.
Yeah, not for another couple of years. I think I
Yeah.
can, I've got a cool piece of software. I actually recommended this to Alex. I don't know if you picked it up, but it says I know about 80% of anything I read at this point. And so,
It's amazing.
I'm just
That's
reading
impressive.
Wow.
pretty much anything anything I want. Some stuff is, if it's more obscure, then I have trouble with it, and other stuff is super easy, and depending on how academic the language is. But it's kind of amazing to just sit there and read. But it's weird because with English, I can look at text very quickly. Like you saw me just read everybody's names, right? Boom, no problem. But it's like I have to focus, and then I have to go word by word looking through it, and then I can make it out. And I'm still translating in my mind as I look at each piece of it. So it's not sort of gelling into larger concepts yet. And the
is
listening
it the picture? Is the pictographs, or is it an anglicized version of
no,
Chinese?
it's the actual
Oh, yeah, you got it.
Hansa. Yeah, the actual.
Is it? Okay.
Yeah. But
Yeah,
the,
pinyin is actually you can't. It's not great for actually learning it. I realize. I'm sure Fraser's saying
Yeah,
feels the
yeah.
same way.
Yeah.
yeah, it's a weird thing though. The purpose of the pinyin is to help you pronounce the words. We should do the show, but at some point I'll have a rant about this, which is just in English, we learn how to pronounce the letters, and then we can say the words, and then that is the bridge to the listening. But with Chinese, there are 5,000 letters. And so in order for you to be able to just pronounce the words that you're reading, you have to learn 5,000 letters. So imagine not 26 letters, 5,000 letters. And then once you can do that, then you can start to read out loud, and then you can start to bridge the connection between listening and reading. Or you can go the other way, which is you can listen to stuff people talking, but you have no idea what those words are as they're written on the page. So it's super weird. Anyway, but it's fascinating, and clearly, I get a workout with my brain. So, all right. So let's push you guys all back into your boxes. Okay, there's me. And here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, December 16th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Neptune's new dark storm. Chang'e 5 successfully returned samples from the moon using the sun as a telescope. Joining me this week on my screen, I got Alex Tichy. Hey, Alex, how's it going?
Doing great, Fraser. How are you?
Good. It's early morning for you. We got a good chunk of the planet covered now.
Yeah, that's right. Rainy Taipei. It's been raining here for 3 weeks.
Yeah.
It's actually kind of
Yeah.
chilly, but
So
what time
different.
is it right now
Not
where
as
you
bad.
are?
9 a.m. A little after 9.
Yeah, totally different from rainy West Coast Canada. All right, we got Carolyn Collins-Peterson. Hey, Carolyn.
Hi there. Hi from the cold, chilly, snowy Rocky Mountains of Colorado.
Featured behind you.
Yes, that's a sunrise view, but yeah.
That's great. And we got Morgan Redberg. Hey, Morgan.
Hey, Fraser. It is nice and sunny here in Texas, or it was today.
Yeah, awesome. All right, well, we're going to get on with the special guest this week, but before we do, I want to make a huge special shout out to our good friends at the Weekly Space Hangout crew. And I know I say this every week, but I just want you to understand that this is a very special community of people who are super space nerds, but they are more than that. They are the executive producers of the Weekly Space Hangout. Unlike most shows, the Weekly Space Hangout is really just a slave to the fans. We show up, we interview who we're told to interview, we talk about the stories we're told to talk about, and we do our jobs. And so if you want to have the kind of just cosmic power that comes with being an executive producer of the Weekly Space Hangout, all you have to do is two things. One, go to the Weekly Space Hangout crew website wshcrew.space. And two, just have the bravery to use your executive producer ship to reach out to any guest you want and have them show up on the show. I know you can do it. So go to wshcrew.space. All right. Speaking of special guests that I had no involvement in inviting to the show, we've got John Powell from JP Aerospace. John, welcome to the show.
Thank you. So I guess I'm representing the West Coast in California here tonight.
Perfect. Yeah. Well, I'm the Northwest Coast. You're on the Southwest Coast.
Okay.
Yeah. But this is great. I'm super excited to have you on the show. It's funny. I seeing that you're going to be coming on the show. I've been following your Twitter feed for years now, and really excited about what you're working on. So for people who don't know what JP Aerospace is, tell us who you are and what you do.
Well, we are actually a volunteer space program. We have a small paid staff and then a large volunteer staff, about 70. And we kind of have two big things. The one big thing that I think we're going to talk about tonight is our whole Airship to Orbit program. That's this crazy idea of finding a new way to get to space. And the second whole thing, which started out as a side thing about 15 years ago, but it's become this giant unwieldy monster,
Yeah.
is our PongSat program. And that's our student payload program that we fly student payloads from all over the world for free. And we take them up to 100,000 feet, let them do their thing, and then get them back. And that's become actually about half of what we do. And then the Airship to Orbit program, the other half of what we do.
All right. So I appreciate you outlining for us today. So let's start with the first part, which is a new way to get to space that doesn't use rockets.
Well,
I guess it's rockets in the end.
Well, there is rockets involved.
Yeah.
But it's just the notion is to think of it as extreme air launch. Instead of Virgin Galactic going from 50,000 feet, and things like the Pegasus going from 50,000 feet, we want to start from 300,000 feet. And instead of starting at 500 miles an hour like a 747, a spaceship one, we want to start from Mach 10 at 300,000 to 400,000 feet and go from there. The thinking is, in 1958, there was a project called Project Shotput. And it was a predecessor to the Echo balloons, the balloon satellites. And what they're doing is taking sounding rockets, like this is an underfunded program, so sounding rockets from the 40s, and deploying balloons at Mach 10 at 400,000 feet. Most of them didn't work. They
Right.
deploy about billions of little pieces. But after a while, a lot of them did. And there was a follow-on program that continued only till very recently, the Robin program. And there's actually been about a dozen of these programs. And they're all about the same, getting balloons to cruise at Mach 10.
So
And
what is
some of
the
that
benefit
falls
of that? Like, why would you want to do such a thing?
Well, kind of two reasons. One is it was a lot of upper atmospheric research. They measure the drag, they measure the consistency. And after a while, they started putting instruments on the balloon. So it wasn't just a balloon with solar panels, with radio transmitters, with sensors on them. And then that also dovetailed into nuclear weapon decoys. That ended up being the big funder of a lot of that work. And the science ended up, even though it started with a science program, it ended up being a rider kind of program. Because when ICBM comes in, it actually deploys quite a few decoys. And these are hypersonic reentry vehicles. Otherwise, they're balloons
Wow.
that look like missiles. And so that's probably why a lot of that testing has gone on. But our thought is, so you got this balloon at Mach 10 at 400,000 feet. And it's just a ball in 1959.
Yeah.
Well, what if you made it aerodynamic shaped? What if you put a little thruster on it? Well, maybe you go a little faster. Maybe you could climb a little higher. What could you do with that model?
Mm-hmm.
What could you do with that model if you add 60 years more technology on there? Could you go to Mach 14? Could you go to 500,000 feet? Could you go Mach 16 at 800,000 feet? That's the question we're going to answer. Can you take it all the way to orbit?
Right.
And I'm here to tell you that I have no idea.
Okay. So,
But the Airship Orbit program is trying to answer that question.
okay. So you actually brought, you've got a model of what this thing looks like. So for people who want to sort of get a sense of what this thing might look like, can you show that model?
I have a
Yeah.
bunch of models. weirdly, the smallest model I have is of the biggest vehicle.
Right.
Endgame vehicle.
Right.
And that's this guy.
Okay.
And they end up being a V-shaped because we discovered it's a high aspect ratio V-shaped vehicle.
Yeah.
Ends up being stable, statically stable in all three aerodynamic regimes, in subsonic, in supersonic, and in hypersonic.
Right.
Which is why it's this shape.
Okay, and so you take this vehicle, what do? You launch it like a balloon, you let it float up?
Well, that's the even crazier part about this. We discovered that this has to be so big. You end up as a gossamer structure that goes at hypersonic speeds, like the Mylar balloons in the 50s. The problem is a balloon like that, or an airship like that, doesn't survive in the lower atmosphere. You get a 5-mile-an-hour crosswind, and suddenly you have 800,000 tons on the side of the vehicle, and then you have confetti.
Right.
And we've actually done that a few times too. So the idea is that you have 3 different vehicles. You have a vehicle, an airship that goes from the ground, a vehicle like this one. This is a scale model of our Ascender 9. It's just under 100 feet long, and it flew about a year ago. And so this goes from the ground to 140,000 feet. Can't get any higher. It's not a supersonic vehicle. It's a big blunt load lifter.
Right.
And it goes to 140,000 feet. And at 140,000 feet, we have actually put our spaceport. And we call it the Dark Sky Station. And we've flown about a dozen of those. Our largest has been about 70 feet long. And it's supported by a series of balloons. It actually looks like this, but if you had 5 arms instead of the 2.
Right.
And we discovered that makes a nice stable platform.
And so for the people who are watching this or listening to this as a podcast, John is sort of showing I'm trying to think what this looks like. It looks like a Zodiac boat with the 2 sides, but I'm imagining then if it's a 5 side, it's more like a starfish in the.
It looks like a starfish.
Right, like a.
They look like just a giant starfish.
Tubular starfish. Yeah. Okay.
Yeah. And they're odd when you watch them take off, because usually when you're by big things that zoom into the sky, they make a lot of noise, a lot of excitement. This, you're right next to it, it's this giant thing, and it just screams away from you and is completely silent.
Yeah.
We had some NASA officials out for launch. It really rather freaks them out, and we kind of enjoy that.
Right. So you've got the station goes up to 140,000 feet and is then what, a stable platform that you can then launch
it's a stable
rockets
platform
from?
that it just stays there, and it's the connection that holds it all together. So you got my hand is the station.
Right.
You got the vehicles come and park, and that's where you bring cargo to and people. So it ends up being a 3-stage system, because then you have the larger, more fragile vehicle that's actually built at the edge of space at 140,000 feet. Or more correctly, it's assembled on the ground, hauled up and inflated.
Right.
So building is maybe over dramatic. That's the vehicle that goes from 140,000 feet. It's buoyant to 180, then slowly starts to move forward. We're not even breaking Mach until we get to a little over 200,000 feet.
And what is your propulsion system at this point?
Right now, we're working on, that's the other big part of this project, is a plasma engine. We've had just over 200 test firings. We probably have literally 800-900 to go, and maybe 5 or 6 more years in that program.
Right.
The idea is that pure electric propulsion, like an ion propulsion, has the efficiency we need, but no thrust, not enough thrust for this. Now, a chemical engine doesn't have enough efficiency, and if you fired it off, you just fire right through the airship and out one side the other.
Yeah.
So we have a hybrid engine, where in an ion engine, most of the power of the ion engine is used to ionize the gas to accelerate out the back.
Right.
We're using what's called a mixed gas ion engine, or we call it just a dirty ion engine, where we use a chemical engine. And the fire from the chemical engine in the combustion chamber is the plasma then accelerating out the back.
Got it. Okay.
So our ion engines that we're running right now can be thought of either the world's worst ion engines, terrible, because instead of 60,000 ISP, we're only getting 1,200.
Right.
And that's a completely sucky ion engine.
Not efficient.
But you think of a chemical engine, and you think, wow, chemical engine that has 1,200 ISP, but the thing weighs a ton.
Yeah.
It can't even lift itself. it's a stupid engine. It's like, why? It's not really an advanced engine that we've thought of that no one else has, because it only has one use. It's the steamship engine.
Right.
You plant it on something that's carrying it, and it goes putt, putt, putt for days.
But it can continue to gain altitude beyond that initial 180,000 feet that it's buoyant to.
And then slowly it's going to accelerate.
Right.
And then by the time we get to the higher velocities, the Mach 10 plus, we're at the altitude of the Shotput balloon, where a little Mylar balloon can go Mach 10. Now we actually have some structure in doing something hopefully a little better than that.
Yeah. And so then is this the vehicle that serves as a platform for the rocket to do the final kick stage to get to orbit?
This is the vehicle, but there's not a separate rocket. The half plasma, half ion engines that we're running, if you turn off the electrical propulsion, you're running a pure rocket engine. And that does the final orbital insertion burn.
Because you no longer have any air resistance at this point, so you don't have to worry about tearing your vehicle apart. Right.
You don't actually want to go Mach until it's like our platforms right now, our balloon platforms, a lot of foam, carbon fiber tubes, paper thin things, and we fly them at Mach 1 on the way down.
Yeah.
That sounds impressive, this light, fragile thing flying at Mach 1. But at 100,000 feet, you've kind of pulled the teeth out of that.
Right.
So it sounds good, but it doesn't really mean a whole lot.
So then, I mean, what's the point? Because like, what is the savings? Because obviously I can imagine that, you get, like with a traditional rocket engine, you have to go through the thick part of the atmosphere. You have to get yourself to that tremendous orbital velocity, 20,000 kilometers per hour. You're going really quickly. So how does this method save you in terms of propulsion, of propellant and costs?
In efficiency wise, it's not very efficient way of doing it. A more instantaneous release of propellant is the most efficient way to burn that propellant.
Yes, of course.
So it's not really that. It's truly changing the nature of space travel. Say you're 3/4 of the way up in a traditional rocket, or just go back a little bit, look at the space shuttle. Except for in a very narrow window, if you lose one of the engines of the space shuttle, it's an LOC, a loss of crew event, unless it happens in a very narrow window near the end. Here, say you're Mach 15, you're only 3/4 of the way through the process, and you have a big engine failure. Well, you go back and you take a look at it while you're drifting back down again. You have a meeting about it.
Right.
You try to get the thing working again. And if it doesn't, well, you float back down to the station.
Right.
Or if you get it working again, you just continue on. That you really don't have in rocketry. Right now, when the vehicle clears the tower, they make that announcement, because that's kind of a big milestone. There's a lot of safety things that you've gotten through at that point. And normally at a launch like that, people are crying. It's all very exciting, especially if you have loved ones on the vehicle. Now imagine you're at the airport. If every time a 747 took off, they had a big announcement, it made it, and everyone cheered and people were crying.
Yeah.
Would you really want to get on that 747?
Yeah. I mean, that's what you're thinking when you saw the Starship landing. You're like, I'll wait for SN9 before I take a trip. We don't have a lot of time left, so I just want to. We need to shift gears then and just talk a bit about your other project that you brought up at the beginning, talking about how you're working with students.
Oh, this is actually the most important thing we did. A friend of ours, Bob Twiggs over at Stanford, it's about 15 years ago, started the CubeSat program. And we both had the same problem. We actually talked about it back then. We flew student payloads, but we only did 2 or 3 a year. Getting someone else's stuff into your stuff is hard. And he standardized it with the CubeSat. And of course, the rest is history. And we thought that was a great idea, totally brilliant on Bob Twiggs' part, but we wanted to take it a step further because we thought it was too big. And we made all our students put all their experiments inside ping pong balls. And if you look at our website, some of them that you open it up and there's 2 data loggers, 18 sensors, a GPS and a camera, all inside their ping pong ball. And some of them are marshmallows. You put a marshmallow mini marshmallow, it puffs up in vacuum and freeze dries. And it's a great science fair project for a first grader.
That's cool.
And we put the announcement out there, we flew 15 of them. So like 15 student payloads in one. And you could do that because instead of integrating them all, you opened up a box, you poured it in the box, and you taped the lid closed. You're done. Well, that was 18,300 ping pong balls ago from 18 different countries, and over 80,000 students have been through the program. It's a completely free program. We don't charge anything for it. We let people fly. We don't judge the experiments. Weirdly, if it's got a GPS, a camera, and 14 sensors, it's a junior high student. If it's marshmallows and plant seeds, some university professor.
Right, of course. Yeah.
Not that I'm judging. You know.
Yeah.
Some little kids, we flew a bunch of Lego minifigure astronauts for a bunch of kids out of Australia. That was really great because it just inspires them.
Yeah.
And then we did cancer research for University of St. Petersburg in Belgium, because they discovered that on one flight, they can get a year's worth of UV that better simulated a year of UV than the artificial lighting could accelerate.
Yeah, I mean, when you think about all of those suborbital rockets that fly all the time, I'm sure many of the experiments that they're testing on those would work quite well on if they can ping pong size their experiment.
Oh, yeah.
Then there's actually a pretty good platform to be able to use it on.
Because a lot of how we pay for all this is, carrying things up for companies, doing their experiments.
Yeah.
And we send literally tens of thousands of kids to the exact same place. I say there's some serious research. There's just some fun to be inspired research. And recently, because it's gotten so overwhelming, it costs us maybe $25,000 to do a PongSat mission. And we do 3 or 4 of them a year.
Yep. And
our backlog is now to 10,000 that we need to fly off.
Wow.
So we started a nonprofit. So we're separating out PongSat to its own universe as a nonprofit agency. So hopefully it can grow beyond us.
So if people want to fly a ping pong experiment, and I highly recommend you follow JP Aerospace on Twitter, because you do a great job of showcasing all of the missions, all of the photographs from those incredible altitudes. Any flat earthers should just be completely, convinced of the curvature of planet Earth.
I get so much flat Earth hate mail.
I know, I'm sure you do. Yeah,
I keep it. I'm going to make it a book.
Yeah, you must spend so much time faking pictures of the curvature of the Earth. But yeah, so if people want to be able to sign up for this program, where should they go?
Oh, go to jpaerospace.com, or actually, we've set up this nonprofit to pongsat.org.
Perfect. All right.
And they just send an email, and that's all it takes. You say, I have a class of 30, I want to do them. I'm just one person, I want to do it. That's it.
Fantastic. All right. Well, John, you're going to stick around and listen to the rest of the space news. So I'm sure we'll get a chance to talk to you again during the episode. Let's move. But thank you so much for taking the time to chat with us today. Absolutely fascinating. So if anyone's got some ideas for some PongSats, now you know where to go. I've got some ideas. I think this is great. Thanks for joining us.
Oh, you're welcome.
All right. Let's move on to the news portion of the show. Morgan Renberg, let's talk. What were we going to talk about? You changed your topic.
No, let's talk about Chang'e 5 because I think this is just amazing. So we have new samples back from the moon's surface for the first time in almost 50 years, 45 years. And I think this has been basically a technical tour de force from the start. It's just extraordinary process. And the speed of it all, I think, has been what has struck me. So in late November, China launched the Chang'e 5 mission to the moon. On December 1st, the lander reached the lunar surface. And here we are on, what is today, December 16th. And we have samples back from the moon. So basically 3 weeks to go from spacecraft sitting in your rocket at your spaceport to samples back from the moon. And the complexity of this mission was just extraordinary. I mean, if you look at the way the Soviets did their sample returns in the 1970s, they were really simple. And this was anything but simple. So, you had the spacecraft launch from Earth, enter lunar orbit. Then you had it separate the lander from the main spacecraft. The lander descended to the surface, scooped up material, packaged that material up, passed that material to the
also did a
ascent
core
stage.
sample, not just scooped off the surface, drill the core sample.
Exactly, yeah. And they packaged all that up. They got it to the ascent stage, blasted that back into lunar orbit, docked it with the mothership, and then sent part of the mothership back to Earth with the samples that then entered. It was basically like a mini Apollo mission done by robots in 3 weeks.
Yeah, it's Apollo 11. It is just piece for piece Apollo 11. Like, the only thing that's different is there weren't people inside it. But you can imagine it being scaled up so that people could be inside this. No problem.
And the benefit of all that complexity was the amount of material that they were able to bring back. They haven't opened it up yet, just landed today, so they don't know quite how much they got. But they're hoping that it's kilograms. I think 2 to 4 kilograms is kind of the working capacity that they imagined. And compare that to the Soviet missions, which were bringing back like tens of grams of materials with their mission back in the 1970s. And so by mastering this automated process, China has, orders of magnitude more ability to return samples from the lunar surface now. And I think this, if nothing else this cements China as basically a first-rate space power when it comes to doing robotic exploration. This is as complicated as any mission that a nation has attempted in the last several decades. And, they're only the third country to bring material back from the lunar surface. And so I think hats off to everybody who worked on this project. China has already committed to sharing these samples with international research teams, which is amazing because they're sampling a region of the moon that hasn't been that well studied. It's similar to the area that the Apollo 12 mission landed at. It's part of the Ocean of Storms. But the Ocean of Storms is like the largest region of the moon. And so the part that China is landing on looks quite different, at least from orbit, than the part that Pete Conrad and Alan Bean landed on in 1969. And so we're poised here to get a whole new tranche of material from the moon that's going to be totally different than the kinds that the Apollo astronauts picked up and the kinds that the Soviet landers returned in the 1970s.
Yeah, and as I said, it perfectly prepares the way for them being able to send humans. When you think about the work that's going on with their Taikonaut missions they've done, building space station, they've pretty much mastered sending humans to space, keeping them alive in space for long periods of time. And then on the other hand, they have demonstrated their ability to perform all of the steps of going to and retrieving something from the surface of the moon. And so you put those two together and you've got humans going to the moon as next.
And I think even more exciting than humans going back to the moon is the opportunities that the robotic missions open up. So they're planning to do this again with the Chang'e 6 mission to launch probably in 2023 or 2024. And, China is the only country that has successfully landed on the far side of the moon. They have communication satellite in orbit around the moon to enable that kind of landing. And so China basically has all the pieces now to send this mission to the far side of the moon to return lunar samples from a part of the moon that we've never gotten a physical sample.
And that's
from.
Chang'e 6, right? Chang'e 6 is going to the far
Chang'e 6, I don't think they've committed to where it's landing, but I would be stunned if they don't try to land on the far side of the moon. And we know from pictures that the far side is dramatically different than the near side. We don't really know what the small scale local manifestation of that is. We know that from a big macroscopic scale, it just looks totally different. But how does that translate to your individual pebble size structure? We basically have no idea.
Yeah.
And now we know that the technology exists to answer that question in just the next few years.
And it's not just this one, of course. You've got Tianwen, which is on its way to Mars right now, and it's going to be a rover, lander, orbiter combo that's going to Mars. They've got an asteroid mission in the works called Jungha, I think, and that's going to be doing sample return from an asteroid as well as in situ resource utilization. So they're going to actually try to make rocket fuel from the surface of an asteroid. So you're really seeing them come out of the gate pretty hard now with their ability to explore the solar system. And I think it's a really great point that you're going to see this robotic exploration at a very large scale to bring a lot of science back, which will really pave the way and really help future explorers. You know, when you do send the humans, you'll have a much better idea of what's the best places to go. Where are the hot spots?
That's incredibly exciting.
Yeah, really terrific. All right. Carolyn.
Yes.
What do you got for us?
Well, I tracked the whole Chang'e thing today too, but as you mentioned earlier, we're going to take a quick look at this quirky storm story from Neptune. And it's not the first storm we've known about. I mean, as you recall, Voyager 2 spacecraft revealed Dark Spot and Dark Spot 2, and there were some other clouds that we saw in 1989. And everybody couldn't wait to see more pictures of it, so Hubble took a picture of it in its first peek at the planet in a few years later, but by then the storm was gone. So everybody's like, what's going on here? Well, since then, several other features like this have come and gone in the Neptunian atmosphere. And Hubble has been tracking those storms. And there's actually now an official program to track them called the Outer Planets Atmospheres Legacy Program. The acronym is OPAL. Well, this storm showed up in Hubble's view in 2018. At least that's when Hubble saw it. And it's big. It's a really big storm. It looks like it could span the Atlantic Ocean if it could cover someplace here on Earth. And we know that it started out in the mid latitudes in the northern hemisphere of Neptune, and then it began to drift southwards. We've seen this pattern in these storms before. So this is a dark vortex. It's a high pressure system. And we know that these form usually in the mid latitudes. They tend to rotate clockwise through the upper atmosphere, and there it is. And after a while, they drift toward the equatorial region and they start to lose their stability due to the Coriolis effect. And so they enter sort of a kill zone. That's what the story kind of termed it today. And eventually the storm just disintegrates. So that's what I think they kind of expect with these storms to do. Well, the story about this one is that it's not doing that. Instead of staying on a southern course, it's kind of turned back northwards, and people are trying to figure out why that's happened. And on top of all that, if you saw in the picture, there's actually another little storm sort of in the same general region. And the question now is this a new storm? Did it spin off from the previous storm that we saw? And nobody's quite sure yet. These are questions that the planetary scientists that are looking this are trying to answer as they study the motions of these storms through the upper atmosphere.
So this idea of the storm moving up and down, I mean, this isn't something that we've seen, say, with Jupiter, the Great Red Spot stays in its lane.
Yeah, it's pretty stable.
Right?
Yeah.
But this spot is actually changing latitude.
Yeah, it kind of reminded me of looking at sunspots in a way, but here's the storm doing this. So it's possible that as they head south towards dissolution, that in this equatorial kill zone, that they're going to fragment and dissolve. But this one could still do that, but they're just not sure. So this casts a lot of light on, how do they form in the first place, which still hasn't really been answered yet. And nor do we really have a strong feel for the structure of the storm. I mean, the vertical structure, right? How far down into the planet to the atmosphere do they go? And one of the questions that the scientists were talking about in this release was, why are they dark? These, if you recall some of the earlier Voyager pictures of these kind of fringy, high altitude cirrus clouds, that sort of thing, those come and go. And one idea that's been floated is that there could be these high altitude dark layers. There's some chemical thing going on, some cosmochem or some atmospheric chemistry that's going on. And if that's the case, then if this is a really high altitude layer, then it could give some insight into the vertical, sort of the top to bottom structure of the storm itself. But right now they don't really know.
Wow.
And so the long-term studies like this OPAL study are really going to give more insight into how these storms move, but I'm not sure it's going to give them insight into what the structure is, how far down they go, what are they doing in the upper atmosphere? Of the best way to understand why they're so ephemeral.
Yeah, I mean, the winds on Neptune are just beyond comprehension.
Oh yeah, I don't remember exactly how fast, but they're much faster than
2,100
Saturn.
kilometers per hour.
Yeah, yeah, it's like Saturn is like 14 or something, and these are 20,
Yeah,
21.
yeah. And so you could just imagine like this idea of the sort of the kill zone of the storms. You could totally imagine that they get too far down and the winds are just so strong that they just can't keep them going. But it is kind of amazing. I love that Hubble every year, like when Neptune is at its closest, Hubble takes a shot, and it does that for all the planets. So we actually get a new shot of Jupiter, a new shot of Saturn, new shot of Mars at every opposition for each one of the planets. And
yeah, this is really cool because in atmospheric studies of these planets, time domain studies are really important. You can't just it'd be like looking at Earth and going, oh, there's these storms, and then 20 years later you look again and they're not. You really need to look really much more frequently. And so, Mars, you can kind of do that with. Neptune, you can do that with, but what you really focus on are these strange little spots, and otherwise the rest of the atmosphere is a little bit more like Uranus in a way.
Yeah, I mean, I guess it's not that big of a difference in the distance. Like when Mars gets to its closest point, it is dramatically brighter than when bigger, Neptune gets to its closest point. You've got like whatever, a 2 astronomical unit difference from the closest point to the farthest point. But still, it's a great opportunity to take these.
What we really like is to have Heidi Hamill talks about this a lot. We want to get a spacecraft out there studying it.
Yes, please.
365 days a year.
Yeah. Yeah, the only serious-ish mission right now is the Trident mission, which is going to go to Triton, but it'll be a flyby. So not even a orbiter. There is a flagship proposal, but it has not gotten any serious support at this point. So
not a lot of traction.
Yeah, so at this point, and then if you think like you're looking at a 10+ year journey to be able to send an orbiter into that system, it's going to be a long time to get some good close-up pictures.
Speaking of mission complexity, yeah.
We need some kind of super balloon, plasma-powered machine to get you out. Can you float all the way to Neptune? Because that would be great.
Oh, see, I would ski on top of the Neptune atmosphere.
Oh, there you go. Yeah, that would be great.
It would still be constant data coming back, Yeah,
that would be perfect. All right, Carolyn, thank you so much. All right, Alex, what have you got for us?
All right, yeah. Well, this is a perfect segue talking about taking pictures of planets and going to the outer solar system. Because what I was going to talk about is this new paper that's come out talking about using the sun as a telescope, basically utilizing gravitational lensing to photograph exoplanets with direct imaging. Now, this idea is not entirely new. This idea dates back to really the late 70s, early 80s. It was first proposed that we could use actually the sun as a giant transmitter to focus a signal and send these signals out. And then in the mid 80s, it was the first time I think that these folks started saying, well, we really could use the sun as a telescope. Remember, think about a telescope is, a big part of a telescope is light collecting power. So if you can use gravitational lensing to focus the light, then you can use the sun basically as a telescope. Now, there are some challenges associated with this. The focal length of this lens is on the order of several hundred astronomical units, really around 550 AU. Now, the viewers are probably aware that that's an enormous distance.
Yeah.
Neptune orbits at 30 astronomical units. So to be able to place a detector at 550, 600, 650 AU is an enormous challenge by itself. But we really could do some phenomenal science with this. What's that? Yeah, no, it's enormously far away. And then you think, you're trying to use this as a telescope. You can't really do much pointing, right? Because you're going to be sitting in one location and, you're going to be moving extremely slowly if you're in orbit around the sun. Otherwise, you'll just be shooting out of the solar system. So this new paper, like I say, not a new idea. What's new about this paper is that they have figured out a way to actually image exoplanets. The light collecting power is fine, If you want to just do, have it be a photometer, like Kepler, for example. If you just want to collect a lot of photons, we've pretty much got that figured out. But this team, Turishev and Toth, I believe their names are, a few years ago, they studied for the first time the point spread function of this gravitational lens. The sun is a gravitational lens. So, with any telescope, the point spread function is very important to characterize. What does a point of light actually look like to the telescope? And sometimes this can have kind of a complex shape. So they studied that in a previous paper, and what they've done this time is figured out how to basically reverse engineer that point spread function and recover an image. And so what we're looking at on the screen, if Fraser's put it up, is an image of this exoplanet, a simulated image, of course. What would the Earth look like if we could image it with this solar gravitational lens telescope at a distance of Proxima Centauri, about 4 light years away?
That's crazy.
This is a 1024 by 1024 image, and basically it takes a year to produce this image. They sample 1 pixel at a time. The image itself is actually sort of projected at a size of, tens of kilometers across. And so the telescope actually moves across this projection and samples 1 pixel at a time.
Wow.
And it's about a 1 minute integration per pixel, and they just kind of slide along and sample the image like that. And so they say it would take about a year. Now, astute observers might start to think about additional technological challenges associated with this. The planet, of course, is not staying still. It's moving around in orbit around its star. And of course, it's rotating as well. So they say, well, these are future challenges.
Not our problem.
This is a single snapshot of the Earth, and practically speaking, you wouldn't be able to do something like this. But nevertheless, the proof of concept is you really can get this kind of resolution, which would be an absolute game changer. To build a physical telescope, I think they estimated you'd need an aperture of 90 kilometers or something like that if you wanted to build a telescope that has this sort of resolving power.
Right.
Now,
that might be more feasible, though.
Yeah.
To build a space-based telescope with an aperture of 90 kilometers, maybe that might be easier than getting a telescope out to 600 AU.
Yeah.
Yeah.
Well, with interferometers anyway, you can get this sort of spatial resolution. Now, we typically think of interferometers as a radio thing. There have been optical interferometers, but usually they have to be very close together because, sort of matching these waveforms in the optical regime is extremely challenging. And so you can't have, unlike a, ALMA or the very long baseline array where you have telescopes that are, many, in some cases, thousands of kilometers apart from one another. You can do that in the radio. To do that in the optical is far more challenging. So anyway, it's a very interesting idea that, being able to recover these images. If a planet is not so close by, say, more like 30 parsecs, on the order of 100 light years away, you wouldn't be able to get such a high resolution image. But nevertheless, a pretty fantastic image, even at those great distances. So, we have to always be thinking, sometimes not just a year or 5 years, 10 years down the line, but thinking on scales of hundreds of years, what we might be able to actually accomplish. If you think about what Galileo and Newton and all of these folks were doing, spacecraft were hundreds of years in the future. Nevertheless, they were really laying the groundwork for the kind of amazing things that we're doing today. So there is still an important role for these really what seems like very pie in the sky ideas. Eventually maybe they actually come to fruition.
Now this concept of essentially using a star as a gravitational lens is used all the time, just not where you don't get to choose the target.
That's right. Yeah. So gravitational lensing, micro lensing, has been something that we have used to identify, for example, rogue planets and even exomoons. My bread and butter. Micro lensing is a similar concept, right? The gravitational lensing, that you can really see these objects when they happen to just be passing, in line from our point of view. That you can probe these very small small masses. And I was going to briefly mention a paper that came out not long ago from my own advisor, or my former advisor in New York, David Kipping, who has brought this same idea of the solar gravitational lens and has said, could we use the Earth as a telescope? He calls it the terrascope. Now, this is a really interesting idea. It's not gravitational lensing anymore, but it is atmospheric refraction lensing. Actually, the atmosphere of the Earth will do this same sort of lensing, and the focal distance is basically the distance of the moon. So it's perfect. You could really build something like this. I mean, we're talking before 550, 650 AU for a spacecraft. That sounds like an enormous technological challenge. But so putting a detector at the distance of the moon, far more feasible, obviously. Chang'e, for example. We're really, this is just a hop, skip, and jump away. Again, seems like kind of, a really out of the box idea, but could be quite powerful.
And it sort of makes you think that any sufficiently advanced civilization at this point has got this kind of technology going, and they're literally watching our planet at this kind of resolution. If they've been around, flying around for 1,000 years, then they've probably got very powerful telescopes scanning every planet they can get their hands on across the universe. It's kind of an amazing idea.
For sure.
Terrific. All right. So Carolyn, you brought up a suggestion for a topic that we could bring up because we are nearing the holidays. You had some ideas for some space-based gifts for people.
Yeah, it was more, if I had a long time, I could give you a list of books and things like that. But I was thinking every year about this time, I get emails from people asking me, what do I get for my baby, my daughter, my son, whatever. And the first thing I always do is say, well, have you talked to them about what they want? What are they interested in? And for books, you have kids that are just getting started in astronomy. You give them things like HA rays, find the constellations, or something like that. Those are pretty easy and straightforward. But people want to buy equipment. They want to buy telescopes. They want to buy binoculars. And it really comes down to finding out exactly what that person wants to look at. If they're a planetary observer, that's going to send you in the direction of a certain kind of telescope. If you're doing deep sky or you want to do imaging, that's going to give you a whole other direction you want to go in. And a lot of times I don't tell people that are just buying things for beginners, start them out with a pair of binoculars because you want to learn the sky. And that's what I use. And I've had telescopes, I've looked through things, I've worked with Hubble, and I still come back to the binoculars when I want to look at the sky.
Same.
So I guess my piece of advice is keep it simple and spend time with them. Find out what they really want. Maybe it's not going to be under the tree on Christmas, but you'll be getting them something a little bit more than just maybe guessing. And don't go to the department stores, talk to some experts about what to buy.
Yeah. People always ask for a telescope guide, telescope buyer's guide. An 8-inch Dobsonian. That's it. That is the beginning and the end of my telescope buyer's guide. That's it.
Yeah. I had a 6-inch. I know what you mean. Yeah.
Yeah. A 6-inch is fine. An 8-inch, if you can afford it. Don't get the 10-inch. Even if you can afford it, it's too big.
Oh, yeah.
And even 8 inches is hard to move around.
Yeah. The Dobsonian is just, you see a bright object in the sky, you take the telescope, you turn it in that direction, and you look at it, and you've got a big piece of glass or mirror that you're able to see this object with. It lets you see the moon, the major planets beautifully.
Yep.
Take it, put it in the back of your car, go to a dark sky site, and then you can see deep sky objects with it. Learn the positions of the night sky. It's going to get you. It's going to be your trusted exploration machine for the universe.
Well, and the beauty of those kind of light buckets is they're not thousands and thousands of dollars.
No.
I think mine was, I don't remember, it might have been $500 or $600 at the time.
Yeah, you can get a 6-inch for about $300. You can get an 8-inch for about even less. Yeah, and then an 8-inch for about $500. And it is a mountain of telescopes. Like when you think about those really expensive, really fancy Celestron telescopes with the big mount and all that, it's the same. It's an 8-inch telescope. It's the same size as one that costs a third of the price. It's just that it's fast and simple to use, and you don't
have to worry about a wobbly mount either.
Yeah, exactly.
That was what I wanted to say. It was just talk to the person, talk to what they want, find out what they really want. And if it's books, you have a million things out there. I've got some listed on my website, but telescopes and equipment, those are a whole other kind of ball of wax.
Yeah.
Really.
Does anyone else have some recommendations for holiday gifts, especially for like last minute as we're 9 days away?
I'm a terrible gift giver.
A ping pong.
A ping pong, a space ping pong.
Who knew you could fit so much stuff in a ping pong ball?
Yeah.
I want all that.
Yeah.
Yeah. Well, in a shameless plug, you can go to the JPA store, and we got T-shirts and books about the Airship program and all kinds of wonderful things. So,
when's
shameless plug.
WSH crew getting their own merch?
Yeah, that's a good question. There you go.
Hey.
All right. Well, we've reached the end of our hour. Thank you, everybody, for joining us this week. I want to go through my co-hosts and give them a chance to let us know where they can find out more and what they're working on. Morgan, you're on my screen. Where can people find out more, and what are you working on?
Yeah, you can always check out my website, morganrenberg.com. And I've been doing a lot of work with SciShow recently, both writing and editing across sort of all their channels. So just go check out some cool videos, and there's a non-zero and much larger than zero chance that you'll see one of mine.
Right on. Alex.
Yeah, what am I working on? I am studying, in particular, the dynamics of planets with multiple moon systems. Particularly, exomoons is really my bread and butter. And for a long time, we've focused mostly on planets with a single moon. And so I'm interested in seeing, what we can tease out from observations when there's more than one moon in the system. So that's what I've been looking at recently. And if people want to follow me and what I'm doing, follow me on Twitter is the best. My handle is just @AlexTeachy.
Carolyn.
Right now I'm working on exhibit copy for this Shanghai Planetarium as part of the Science and Technology Museum there. So they've sent me all of their copy. It's been translated from Mandarin to English, and I'm working on visaging it into English.
Oh, good.
And it's more fun than, it's actually very amusing. I should talk to you sometime about this. Anyway, if you want to follow me, you can look at my blog. I'm at thespacerider.com.
Excellent. All right, and John, you stuck around for the show, so you get another chance to plug what you're working on. So if people want to find out more, where should they go?
You should go to jpaerospace.com, and also our Twitter feed, because I try to post 5 or 6 pictures a day. Our next mission is May 2nd. We have 480 PongSats all signed up, and we're hoping, we've called that mission, made all the patches, the Thrive mission. So we're hoping we're moving forward. And we're finished up this airship. This is just a model of it. About 6 months ago, and we can't fly it because we can't get the team together, but this is the next one.
Wow.
Heading into the sky.
That's incredible.
As soon as we can.
All right, so I've got one quick thing to mention to everybody, which is that we're not going to be doing the virtual Star Party at its regular time. We're going to be doing the Star Party on the 21st of December, and it's going to be at a funny time. It's going to be at 1 p.m. in the afternoon, and that's because it lines up perfectly with the closest time of the Great Conjunction with Saturn and Jupiter. So we were lining up a couple of astronomers, Corey Schmitz in Africa, probably a couple of people in Europe, and we're going to try to bring you a live stream of Jupiter and Saturn in the same eyepiece. So we'll have more information on my YouTube channel as we get set up for that. But that'll be on the 21st. And we'll probably go live about an hour before and sort of see what we can do in terms of bringing images together. But I also anticipate that this isn't going to happen. So you know how it goes with live astronomy observing. And of course, you can find everything else at universetoday.com. Now, if this is the last episode for the holiday break, so we will all be gone. I don't even know how long we're going to be gone for. We'll be back at some point, but I hope all of you have an incredible holiday, safe holiday, and we get to see all of you again in the new year. All right, putting everybody back here on the screen. Thank you, everybody, for joining us today. Thank you to my co-hosts and special guest. Thanks to all of the moderators in the chat. Thanks, of course, to Nancy Graziano for keeping us all super organized. We really couldn't do this without you, all of you. Really appreciate your support. And we will see all of you next time. And I don't really know when that is. There you go. Nancy is saying January 6th. So we'll see you on January 6th, 2021. That'll be a good year. All right. Thanks, everyone. We'll see you next year. Awesome.